Hello and welcome to my presentation on current electricity, which is really to do with revision for year 11 and indeed for year 12 students. So let's get into it. Here we see the contents, and I'm going to go as far here as resistors in series and parallel and some review questions. This is FES physics. Why FES physics? Well, because I am a physicist. Get it? Or is it just a phase I'm going through? However, there I am with my phase, and we have a circuit here. And when I was teaching year 7 pupils some years ago, I would mark a circuit like this on the playground using chalk. Pupils would pick up a piece of chocolate or a sweet from other pupils in the cell or the battery and walk along to the lamp. They would pass the chocolate to other pupils in the lamp, who would then eat the chocolate. The carriers, the electrons, would then walk back to the cell, empty-handed, to pick up more chocolate. Hugely unfair, you might think, but in the end, I made sure that everyone had some chocolate. So, electrons carry energy around a circuit. And this is one model of current electricity, but isn't it interesting as to how our models in science develop and become more complex from key stage 3 and even before that up to GCSE, A-level and then university. Now here we have an image on the left hand side of a piece of metal. We have positive metal ions, this lattice. Why is it a lattice? Well, that's the structure of the material. These positive metal ions are not free to move randomly. They can vibrate, but it's the electrons, the sea of electrons. Each metal ion has contributed an electron, and this sea of electrons can move in random directions through the metal. Electrons, of course, have a negative charge. If we then, on the right-hand side, put a battery, a cell in position, then the electrons are still moving at random, but there's a flow of electrons towards the right-hand side, as I've indicated, towards the positive of the battery. But don't forget, and I'll come back to this point in due course, conventional current is in the opposite direction to the flow of electrons. Okay, few definitions. The unit of charge is the coulomb, and I've given an indication 2.5 coulombs, or the abbreviation 2.5 and a capital C. An electron, single electron, has a charge of minus 1.6 times 10 to the minus 19 coulombs. Worth remembering that. So on the right hand side, 1.6 times 10 to the minus 19 coulombs is equivalent to 1 electron. So I then follow through, and by a little bit of mathematical jiggery-pokery, we can see that 1 coulomb's worth of charge is about 6.25 times 10 to the minus 18, 6.25 times 10 to the plus 18 electrons. So 1 coulomb's worth of charge is indeed a lot of electrons. Electric current here, well, measured in amperes, or amps as we usually say. And here I've indicated that conventional current is in the opposite direction to which the electrons are flowing again. Now, in the 18th, 19th centuries, scientists guessed that something was moving in a circuit, but they got the direction wrong. In the meantime, the link between electricity and magnetism had been established, and rules like Fleming's left-hand rule were established, which worked with the direction of conventional current. So we still stick with Fleming's left-hand rule, and so we have to know about the direction of conventional current, which is opposite to the direction of flow of electrons. And you might be saying, well, can't we just change things, change the rules? Well, yes, in some countries this has happened, but hey, this is the way we're working today. So let's look at an amp in a bit more detail. What's a definition? Well, in my circuit that you'd see on the left-hand side, when a current of 1 amp flows, 1 coulomb of charge will pass any point in the circuit in 1 second. So we can say 1 amp is 1 coulomb per second. The symbols we use for current is I, it's from the French intensité. I equals Q. Q is the symbol we use for charge, and T is time. I equals Q over T. On the right-hand side, Q equals I times T. Also an equation that's well worth remembering. Voltage or potential difference. Right, this is a little bit more involved. And I've shown you a cell, a lamp. Now, let's imagine that we've got electrons flowing from the cell upwards and down this slope, coming downhill, perhaps losing energy like you would do if you were riding a bicycle downhill. At the top of the slope, the electrons have high energy, and another word for energy is potential. High energy, high potential. And we'd say that potential was plus 1.5 volts. As the electrons pass through the lamp, on the other side, at the bottom of the slope, or in fact just after the lamp, the electrons have a low energy or a low potential. So that's 0 volts. And is there a difference in potential across the lamp? Yes, there is. And the voltmeter measures the difference in potential, or potential difference, or PD. So potential difference or voltage is all to do with energy. And of course, we know that in a lamp, electrical energy, whatever that is, and I'm avoiding talking about that, but electrical energy is converted into heat energy and into light energy. So let's look at the definition at the bottom. 2 points are at a PD of 1 volt if 1 joule of electrical energy is changed into heat and light energy for each coulomb of charge passing between the 2 points. Another way of saying this is that 1 volt is 1 joule per coulomb. Okay, we've got that. Let's put some symbols in. V equals energy. I've just used the term energy. I could have used something like delta E. V equals energy over Q. Q, remember, is the symbol that we use for charge. So rearranging that, energy equals Q times V. Also another very useful equation. So we've established 1 volt is 1 joule per coulomb, 1 amp is 1 coulomb per second. Now let's look at this. There's an equation that you might have come across before, V times I. Well, V times I, in terms of units, V is joules over coulombs, current is coulombs over seconds, coulombs cancel to leave joules over seconds. Joules per second. Well, 1 watt is 1 joule per second. 100 watts is 100 joules per second. A 100-watt lamp bulb will convert 100 joules worth of electrical energy into 100 joules worth of heat energy and light energy in 1 second. So joules over seconds is power. So power equals V times I. And that's an equation you may well have come across, particularly in year 11. It may well have been thrown at you without really an explanation. Learn that, remember that. Okay. Now, what we have here is a circuit, and we've got down at the bottom with a voltmeter across it. Remember, voltmeters are always in parallel. Ammeters are always in series, and we've got a resistor there in the middle, and on the right hand side we've got a variable resistor. This is one of those things that you've probably come across in class with a slidey contact. Now, 1 cell, or maybe 2 cells you could have in a circuit like this, but by sliding the contact, from one end to the middle to the other end, we can get 3 pairs of readings for V and for I. And when we do this for a fixed value resistor, we divide V by I and we get R. That's the resistance of that component, of that resistor, in ohms. And again, you've probably come across this kind of circuit before. Here we see something similar, and with this kind of circuit, well, if we were to increase the potential difference, if we were to have more cells in there, we would have a bigger current. V is directly proportional to I. That means if the potential difference goes up, then the current goes up. And this relationship is known as Ohm's law, named after a German physicist. Originally he was a school teacher, but then moved to work at a university, Georg Ohm. Now, if we have that proportionality, we can move to an equation by putting in a constant of proportionality, which in this case is R. So V equals IR. The resistance in ohms, which could be maybe 10 ohms, and we see that familiar symbol for ohms. Okay, the unit of resistance, we've said all of that, but the important thing here, and this sometimes comes up in exam questions, another unit for the ohm, because R is V over I, would be volts amps to the -1. Cunning. So, what is this? Oh, it's an ohm symbol on wheels. What is it? It's a mobile ohm. Groan. So what's this? Ohms under the hammer, a BBC television programme in the UK. And what's this? It's a, yes, that's right, it's a broken ohm. Sorry about that, folks. Now, electrical resistance. Resistance is the opposition to the flow of current. If we have a large resistance, we have a small current. If we have a small resistance, we have a large current. And there down below, I've said a little bit more, it's again about Ohm's law and that relationship V equals IR, or V equals R times I. And okay, we've got V equals IR again. Now, the factors affecting resistance in a conductor, a wire, a metal wire. Well, the length of the conductor. If we increase the length, we increase the resistance. Now, one way to think about this is if we have a long hose pipe, there is more frictional resistance to the flow of water, so the flow rate is lower, and so we say the resistance is higher. So that's my analogy with the flow of water through a pipe. The width of a conductor, well, the resistance is inversely proportional to the cross-sectional area, A, of the conductor. Again, with a wider hose pipe, we get more water through, all other things being equal, the flow rate is higher, and so if the flow rate is higher, we say the resistance is lower. Temperature, well, we'll come on to temperature in a moment, but if the temperature of a metal increases, then the resistance increases. And you may have come across this, and it's all to do with the vibration of the positive metal ions in the lattice. Okay, now resistors in series and then in parallel. Look at the top left-hand diagram. Two resistors in series, R1 and R2, potential difference across them, V1 and V2, and potential differences in a circuit add up, so that V is potential difference across the cell, which is the same as across the two resistors. V equals V1 plus V2. Okay, and of course it's the same current through each resistor. So can you see the two equations I've written? V1 equals I times R1, V2 equals I times R2. Okay, down below we've got another circuit, and we're asking ourselves, what is the combined resistance RT such that we get the same current I from the same cell as we did with the two resistors R1 and R2. So here, V equals I times RT. And on the right-hand side, again, we said V equals V1 plus V2. So I times RT equals I times R1 plus I times R2. And a little bit of cancellation leads us to RT equals R1 plus R2. So when we have resistors in series, we add their values. And we could have 3 or more in series, and we just add them sequentially. Now, the good news is that you don't need to prove this relationship, usually. You'd be either given the equation or you're simply expected to know it. But I think following that argument through is good for you, good for your soul, if you have one. Resistors in parallel. Look at the top diagram. Let's just take our time. Two resistors in parallel, 2 voltmeters across each of them. And for the top resistor R1, the current I from V equals IR, I1 equals V1 over R1, and I2 equals V2 over R2. Now, the potential difference across the cell is the same as across each resistor. It must be. It's an equivalent position. So V equals V1 plus V2. Now, when the current comes to the junction, I'm talking about the top diagram, when the current comes to the junction, current I splits into I1 and I2. So we can say I equals I1 plus I2. Now, down below, we're asking ourselves, what is the combined resistance RT such that we get the same current I from the same cell as we did when we had 2 resistors in parallel? Okay, well, from this bottom circuit diagram, I'm saying V equals I times RT, so I equals V over RT. Well, let's move to the right-hand side of the screen here. I equals I1 plus I2. So let's substitute for I, it's V over RT, substitute for I1, substitute for I2, and we get V over RT equals V over R1 plus V over R2. The V's will cancel so that 1 over RT equals 1 over R1 plus 1 over R2. If we had a third resistor, it'd be plus 1 over R3. So resistors in parallel, we get the combined resistance using this formula. Right, now I've got some review questions here, and these are fairly straightforward, but it'll help you to be a little bit more familiar, to become a little bit more familiar with these equations. So give these a go. Pause, give them a go, and then check your answers. Yes, with my answers. And thank you very much. That's Fez Physics. Keep working, and goodbye for now.